All right, let's dive right in. Welcome to this explainer. Today we're getting into the sheer awe-inspiring mechanics of hydropower. We're talking about the massive machines, those unbelievable civil engineering marvels, and the incredibly intricate fluid dynamics that basically make hydropower the absolute king of renewable energy. If you've ever stood in front of a giant dam and wondered exactly how the still water sitting on one side turns into enough electricity to power an entire city on the other, well, you are definitely in the right place.
Before we get into the nuts and bolts, we really need to wrap our heads around the scale here because it's staggering. Globally, there is over 1,250 gigawatts of installed hydropower capacity. To put that into perspective for a second, hydropower accounts for a massive 71% of all renewable power on Earth. So it's not just a piece in the puzzle, it is literally the foundation of global renewable electricity. It alone generates about 17% of the world's total electricity across all sources.
Just think about the Hoover Dam out in Nevada. It's an absolute icon of civil engineering, right? Hydropower at this kind of massive scale relies on accumulation reservoirs, which require huge financial investments and wildly complex topographical studies just to build. The Hoover Dam uses 17 parallel turbines, 15 of which are these massive Francis turbines, working together with a 590-foot maximum drop. And that setup produces roughly 4 billion kilowatt-hours of electricity every single year. What's really smart about having multiple turbines running in parallel like this is that it allows operators to just shut some of them down during periods of low demand or for routine maintenance, completely avoiding having to shut down the whole plant.
So let's actually trace the journey of the water to see how this whole system builds up potential. It all starts up at the still surface of the upper reservoir, where the water is just holding immense potential energy. From there, it rushes down this massive pipe called a penstock. It blasts through the turbine, spinning the runner, which is directly connected by a shaft to a generator. But the water's journey doesn't end right there. After leaving the turbine, it enters an expanding tube called a draft tube. This draft tube actually slows the water down and recovers pressure before finally discharging it into the downstream river, which we call the tail race.
Now here's where it gets really interesting. How do we actually measure the energy in a system like this? It all comes down to a concept called head. You can kind of think of the whole system as a slightly leaky bucket of efficiency. Your gross head is the total physical elevation difference between the upper reservoir and the lower tail race. Simple enough. But as that water comes rushing down the penstock, friction happens. You get these irreversible energy losses, literally just from the water rubbing against the inner walls of the pipe. So what's actually left over the exact moment it hits the turbine is called the net head. And this is crucial. When engineers calculate how efficient a turbine actually is, they only judge it based on the net head. They don't blame the turbine for the friction lost in the pipes beforehand.
Okay, so when that water finally reaches the bottom, it's going to smash into one of two completely different families of dynamic turbines, impulse or reaction. And wow, you can immediately see how drastically different they look. On one hand, you have an impulse turbine, which kind of looks like a high-tech water wheel covered in little buckets. And on the other hand, you have a massive propeller-style reaction runner that honestly looks like it belongs on the back of a giant cargo ship. You might be wondering, why do we even have these two totally different designs? Well, it essentially boils down to geography and physics. Impulse turbines absolutely love a really high vertical drop, a high head, but they can operate beautifully with a very small volume of flowing water. Reaction turbines are the exact opposite. They can do their job with much less of a vertical drop, but they are incredibly thirsty machines. They require a massive volume flow rate of water just to function efficiently.
All right, let's look closer at Category 1, impulse turbines, and specifically the famous Pelton wheel.
So this was invented by a guy named Lester A. Pelton way back in 1878. The impulse turbine works by squeezing water through a tight nozzle, which converts its energy into a super high-speed jet. This jet then smashes directly into these bucket-shaped vanes. And here's a wild little detail. Legend has it that Lester Pelton actually modeled the central splitter ridge of these buckets after the nostrils of a cow's nose. I mean, no way, right? But it ingeniously splits the water jet right in half, turning the flow almost completely around. Now, you'd think turning it a full 180 degrees would be best for maximum momentum transfer. Actually, scratch that, because if you do that, the water literally splashes right back into the back of the next bucket coming around. So engineers perfectly calibrated to turn the flow about 160 to 165 degrees, which avoids the splash and yields up to an amazing 90% efficiency.
Moving on to Category 2, reaction turbines. This encompasses the Francis and Kaplan models.
Unlike an impulse turbine, which gets blasted by an open-air jet of water, a reaction turbine operates completely submerged. It fully fills its outer casing with swirling water and relies entirely on a massive pressure drop as the fluid passes through the blades. And this brings us to the most famous of these machines, the Francis turbine. Developed in the 1840s by James B. Francis, this is the exact type of machine you'll find powering the Hoover Dam. The physical size of this radial flow runner is just staggering. If you want a good mental model, you can think of its geometry as being somewhat similar to a centrifugal pump, but running entirely backward. Water enters from the outer edges, gets forced inward, and spins those colossal blades as it goes.
And then we have the other main type of reaction turbine, the Kaplan and propeller turbines. These use an axial flow design. If you've ever had a window fan sitting in your bedroom window and a sudden gust of wind from outside makes the fan blades start spinning backward on their own, well, you've basically just witnessed the basic operating principle of a Kaplan turbine. Because they sit directly in the flow of the water, they are absolutely perfect for low-head, high-volume river conditions.
But listen, you can't just dump rushing water onto these massive blades and hope for the best. The flow has to be managed with absolute precision. Engineers use these fixed pieces of metal called stay vanes, along with adjustable ones called wicket gates, to perfectly angle the incoming water so it hits the runner blades exactly parallel to their edge. This prevents these massive, energy-destroying shock losses. And here's a really fascinating detail. The turbine runner is actually designed to impart just a tiny bit of what's called with-rotation swirl into the water as it exits. Leaving just that little bit of swirl in the water actually makes the downstream draft tube operate at optimum efficiency. It is literally a delicate three-dimensional balancing act.
So, that brings us to Section 3, selecting the right machine using something called specific speed. With all these incredible, super specialized machines available, how on earth do engineers mathematically decide which gargantuan piece of metal to install when they evaluate a brand new dam site? They don't just guess, obviously. They use the ultimate engineering cheat sheet, a metric known as turbine-specific speed. This is a single, dimensionless number that takes into account the rotational speed, the shaft power, the fluid density, and the net head of the site. Once you crunch the numbers, the result instantly dictates your engineering choice. If your specific speed is less than 0.3, boom, your site needs an impulse turbine like a Pelton wheel. If it falls between 0.3 and 2.0, you are looking at a Francis turbine. And if it's over 2.0, you definitely need a Kaplan or propeller machine. It's just a brilliant mathematical shortcut to unlocking maximum efficiency.
Finally, let's explore Section 4, run-of-river, which offers an alternative path.
So far, we've focused heavily on these huge accumulation dams, but as amazing as they are incredibly expensive and, honestly, carry massive topographical and environmental complexities. That leads us to pivot to a lower-impact alternative, run-of-river plants. These installations don't use giant water reservoirs at all. Instead, they just divert a portion of a naturally flowing river right into a turbine and then simply return the water back to the river a little further downstream. But run-of-river plants face a pretty rigid mathematical limitation. Because they lack that massive vertical drop of a huge dam, they have to rely entirely on the river's existing kinetic energy. And the physics here say that power potential is proportional to the cube of the river's velocity. Plus, only about 60% of that velocity cubed power is even theoretically available for capture. So if the river runs slow, your power drops off a cliff. Furthermore, you can really only build the plant for an average flow. If a huge seasonal flood brings excess water, you just have to let it bypass the turbine entirely.
And that leaves us with a pretty profound engineering trade-off. On one side, we have the technology to extract enormous, totally reliable energy using awe-inspiring machines like Francis and Pelton turbines, but they very often require us to reshape the Earth with giant dams. On the other side, we have these lower-impact run-of-river options that rely purely on the whims of natural kinetic energy, capturing far less power overall. So, when balancing massive, reliable energy output against topographical and environmental impacts, what will the footprint of our renewable future actually look like? It's a fascinating question of geography, physics, and priority that engineers are still trying to solve today. Thank you so much for joining me for this explainer. I really hope you walk away with a newfound appreciation for the incredible mechanics of hydropower.